Hi, Dr. Petros. I'm Prateek. I'm Christos' student.
Oh, good.
Yeah, I'm filling in for him. I might not be able to make to this meeting.
Okay. So am I supposed to start now or let me know?
I think yes, Petros, get started.
All right. Well, good morning, everybody. Today we're going to say a few things about what we have been doing here at UNR, and in particular in terms of the simulation and game environment that we are developing with Hyung-Jin and Christos and students. So here's some outline of what we'll talk about. So I'll say a few things, general things about the simulation type of efforts that we're doing, and then I'll pass it to Hyun-Jin, who is going to talk in more specific terms about the simulation tools and the various updates he has, and further give us some indications of how we can use these simulation environments to deal with problems of various sorts. For example, checking what happens with if you have attackers doing some image attacks, or how you can test some robust control designs using these environments and so on. Right, so this is the picture that we have from the proposal, and we are going to look at trying to implement all the learning-enabled autonomy stack for testing and also being able to do verification and fault diagnosis, which are the technical challenges 3 and 2. So what we will be doing is getting inputs from all of these boxes and trying to implement them in our simulation environment. Now, in terms of simulation environment, there's been lots of developments in the area of autonomous vehicles, autonomous cars. So Tesla has been using all these photorealistic simulations, and primarily using a virtual reality game engine kind of environment to test things out. Other companies are moving into that direction, like MATLAB has been providing tools that connect to the Unreal game engine. Also, VMO is doing a lot of this type of simulation environments, virtual reality environments. And so what we're trying to do here is use this type of VR game engines, which have become the industry standard, to develop our testing tools, and in particular trying to implement the learning-enabled autonomy stack, which is to be developed in TC1. And all of that would be with our VR game environment. So this is a picture of the movie that we kind of have as our vision of developing our air taxis and air vehicles, this urban air mobility. And for that to be happening, we need to have situations where simulations where we can capture cluttered type of environments like in the movie, and be able to test all these perception and planning control methods within this cluttered type of environments. And so there are some projects available now that we can take advantage of and use their simulation environment. And for example, Carla is one that we have been we have started to use in trying to get a cluttered urban environment. And so here is a picture of this project that shows this Carla type of environment that is available to us, and we can do certain modifications to make it more realistic and put in more vehicles, also flying vehicles, as you see here, this flying Tesla car moving around. And this is related to the Unreal simulation, Unreal software version 4 that we have been developing, using to develop this kind of environment. So here's this just to say that because lots of the techniques that will be developed will be based on some stochastic optimization, it is very important to be able to simulate accurately. So we do like to have quite accurate simulations to have a good sense of how the algorithms perform. So here is another simulation VR environment of using the real version 5, okay, which is a very accurate and very realistic type of scenario that we plan to use in our analysis. And Hyung-Jin has started doing some of that, and he might be able to talk more about it later. And so this is some pictures of what can be done. So we are looking at this type of things and integrating some of that into our facility. So this is a point where I think I will pass it to Hyun-Jin, who is going to say more specific things about the simulation tools that we are developing, and he will be more accurate in all of this discussion. So I'll switch with Hyun-Jin right now.
Good morning. I'll go over some detail about this simulation tools. So we are using this ROS, Robotics Operation System, as a middleware to connect all the components. The Unreal Game Engine has a many projects that is developed for autonomous car and autonomous aerial vehicle that include Kala and AirSim. And then from here, we can obtain this photorealistic camera simulation. You can actually change the weather condition or lighting condition, and you can even simulate the rainings and the wet surfaces. And then also the camera lenses deflection can be also simulated in this environment. And then we can implement other thesis algorithm as a node that receive the data from the Unreal engines in real time. And then you can, this Unreal game simulation is connected to more realistic dynamic simulator, ordinary differential equation solver, that is a gazebo, but we already have worked on to replace this gazebo in case when we need MATLAB Simulink, because we are using this versatile middleware called ROS, so we can actually do this. MATLAB provide this interface from between MATLAB and ROS. So that's the idea. And then for real future real vehicle implementation, we need to think about what autopilot software that we can use. I know that in Naira's group, they have used this ArduPilot to implement L1 adaptive control. And also in Christos lab, they are using both PX4 or ArduPilot. So at this stage, I connected this component to see that actually those can be connected and then perform some good looking simulation. As you can see the next slide. Here, what we see is this part, this is a gazebo simulation. Gazebo simulation is a little bit different from our typical way of running MATLAB Simulink simulation, because in MATLAB Simulink simulation, we usually need to write down equation of motion, but in this one, you directly work on more inertial matrix and to give the position of the actuator. And then also you can set the dynamics of the actuator in the gazebo, and then it solve that rigid body dynamic equation by itself. So you don't have to really write down those equations. However, but as a control engineer, we are more familiar with the MATLAB and also writing down equation of motion. So we have a method to actually use MATLAB Simulink model. I'll show that in later, but however, here it is what you see is that this motion in the gazebo simulator is connected to the vehicle in the Unreal game engine. And then the Kala project developed by using Unreal game engine provide this LiDAR sensor and the ground truth segmentation. And also you can query the information of the surrounding object, including the moving cars. And then the part of the PX4, it has the user interface that provide waypoint navigation tools and everything. So I think that we are almost ready to implement the algorithm that's going to be developed in TC4 and others. And then another illustration video shows that from this gazebo simulator developed by PX4, you can even simulate the transition from multi-rotor mode to fixed wing mode, like this. And although we will be able to use MATLAB model provided by NASA, but before that, we try some customizing the V2 vehicle by adding formal propellers so that it looks more similar to NASA's lift and cruise. But I had to use the controller already developed by PX4. So actually, when I add these 4 propellers, actually they are following the same command for the already existing propellers. So, but although it is actually simulating the 8 propellers vehicle's dynamics, and then the default controller provided by PX4 is a usual P.I.D. And then in this case, I was lucky to have that working even without changing any game. Okay, and then let me move on. So to give you the idea how PX4, the position of the PX4 in the industry is that people actually use PX4 as a template to develop their commercial level vehicles that include these two. For example, this vehicle's wingspan is 4 meters, so it is pretty big, although it is not comparable to human passenger carrying vehicle that we are trying to develop. But I think that a PX4 is I want to just emphasize the PX4 is not a toy level or hobbyist level. It can be actually developed further into commercial level autopilot software. Okay, finally update. So because we are waiting on NASA's Simulink model, I did some work on to interface our modular simulation structure to have this MATLAB Simulink. MATLAB Simulink started to provide this ROS interface, I think, about 3 or 4 years or even 5 years ago. So it is actually pretty mature state at this moment. I think that at this point, when we are not sure about the control algorithms and also simulation model, then in that case, I think that we can put both controller and vehicle dynamics within the Simulink blocks. An example that I made just has actually second order dynamic model and all the XYZ translation and then the 3 body angle dynamics are kind of independent in the second order model. But however, this proved that we can actually interface the upcoming NASA's vehicle dynamic model. I remember that they are developing this vehicle dynamic model using MATLAB Simulink. And this is the one, and then we are looking forward to get NASA Simulink model or other MATLAB model. And one minor technical difficulty that I expect is that if you want to run Simulink model in real time, actually you need to set the pace to run the simulation time is equal to the real time world clock time. But in case your dynamic model is very complicated and maybe the computer might not be able to keep up with the pace set by this, but I think that usually ODE dynamic with integrators are not heavy in computation. So I hope everything will be fine, but we are looking forward to NASA Simulink model. This is one update. Another update that we have is inspired by the sensor configuration provided from SNC. We try to set similar sensor configuration with this flying car. We added maybe one or more two camera, but only the major difference from the typical autonomous car is that in autonomous car, they usually get the LiDAR sensor signal for 360, but I just try to mimic the just front LiDAR sensor signal. Looks like that's what they are, what SNC peoples are thinking. So that's what we made. And then using this, I made my first pass real-time path planning using A*, very basic, but the popular one. And then also we use this Octomap to get the occupancy grid. And at this point, it's just 2D path planning. You can actually see that the path is real-time calculated. As you can see, the path is changing. But I did not have actually the path following controller yet because I needed more time. But I think it is not very difficult, and especially at this moment, I'm just using the MATLAB's second order model dynamics. So I'm following that. It's not going to be challenging yet. So once we get more interesting dynamic model, I think that's the point where we actually work on together for path following control too. So, and I think that I've not been very convincing to say how this game environment can be useful. So I will just introduce several use cases of this game environment in research, and also I have some idea that I want to present in AIAA SciTech invited session, and also I'll conclude this with future work on the simulation tool. So work that I've been interested in is actually is related to expertise of Professor Bo Lee. Adversarial machine learning has been, I think it was, people were actually very interested with this topic. I think I do not know the trend at this moment, but people were very interested about this approach. Basically, if you have the adversary, and then using this framework with the adversary, then you can have an opportunity to robustify the machine learning tools. What you see here is that by adding the small perturbation, actually you can make the machine learning classifier confused. And then there are many papers published in this direction. One of them was this paper. This paper tried to add this adversarial patch to attack the detection of the car from the camera images, but this existing method is an offline method. It has to run through the usual iterative optimization to get this adversarial patch. So what I proposed was we want to do this everything in real time using the neural network that generates such images, and then you can choose a target to fabricate those images, and then we've been trying to improve this performance as we go through many rejections, and finally got accepted to robotics and automation ladder. But one idea that I had was if we can evaluate the attacker's capability, then based on the evaluation, sometimes we can switch on and off that attacker so that the attack will be more efficient and the attack will be more stealthy because we are not going to use it all the time. So that was the idea. The point is that using the simulation framework that connect the Unreal game engine, gazebo simulator, and also other machine learning components or controller can be implemented using ROS, same middleware. And in this example, I had probably 7 different nodes running in real time, and then we were able to make it run. And then furthermore, we first test with the simulation, and then actually we tested with the real robot too. But this transition from the simulation to the real indoor UAV didn't take much time because we already developed everything, and we are using the same middleware in this real robot implementation. So this is a video that shows in the normal operation, it goes the UAV here goes the target as we intended. But when you train it using this framework, and actually you can add very small perturbation and you can let it crash to the ground or to the building, depending on the learned actor and critic in the reinforcement learning. And then we tested it with the real robot too, using the same software that we developed using the simulator from the simulation. And it took like 5 minutes to do this fully training because we are basically employing the white box attack method. We have access to parameter of the model, so the running was long. Okay, and we had it with the car environment with multiple tracking, object tracking situation. We'll go over that. And then now, upcoming work from our group led by Petros is that we found this paper published already 2 years ago, and then they tried to interpret the error from machine learning as the noise coming into linear model. And then we think that we can quantify the robustness against the error in the perception and the performance using usual system norm, H norm here. And then our test scenario is very simple, just tracking the object at the front using these camera images. And then now how this work going to be new compared to this work by Dr. Dean in Caltech or Berkeley. Do you remember where they're from? Berkeley, I think Berkeley. Is that we are going to add this online estimation of uncertainty in the object detection. There are many papers out there doing the same uncertainty estimation, especially with the YOLO. And then in this example, you can see that this person standing is, I think this 50% of his body is kind of occluded by a wall. And then comparing the variation of the coordinate out of this YOLO is previously about 7, it becomes 11 because of this occlusion. So there are ways to estimate such uncertainties. And then the idea is similar to simplex architecture studied by Professor Louis. The idea is that we want to have 2 different robust controller has a different sensitivity against the error in the perception, and we will use a simulation to set different weather condition, different lighting condition, and then we will borrow the tool developed by machine learning researchers in uncertainty quantification. And then it is simple. We just want to implement the common sense that humans get cautious when they are uncertain about the environment. I think that this is very simple implementations of the humans' interesting behavior in considering uncertainty when they move or when they make decisions. But I think that this should work. So we are looking forward to present this idea in LIAA SciTech invited session organized by NIDA. Okay, the future work on the simulator. We already have GitHub repository, and then I added science students, and I added some NIDA students to this repository because I have the copy of the proposal in this repository, so I keep this as a private repository. So let me know when you want to use this. We spent some time and we spent some effort in organizing this GitHub repository to be in better shape, but still it's very messy. But I believe that as we get more collaborator and getting more feedback, we'll improve this. And then the second step that we want to do is we eventually need to replace the flying car, although I like this flying car because it is inspired by the classical movie that I like. But I think that we're going to use this VTOL. And in this website, we can buy such 3D model with the price range of about $50. So I do not know about copyright at this moment, but I think we'll try to use those. And then the more important step that I'm going to work on is I made very most simple formal path planning with this occupancy grid, but I think that we need to have some basic functionality, even if borrowing off-shelf methods. So the other step that I want to do is that I want to implement some sensor fusions that's going to be similar to the environment map show up by the autonomous car industry. Basically, combine the light sensor and the occupancy grid. And also, we want to integrate the object detection from the camera sensors. And then the next step will be we want to predict the velocity of the moving obstacle in the environment. First step is, as usual, the Kalman filter to get the velocity of the moving obstacle. So those are going to be upcoming feature with the simulation environment. Thank you. And this is the group led by Petros. Do you want to say anything about here or?
No. I think Hyung-Jin has been running the whole show here for us, and we're hopeful. We're happy that we have also other graduate students joining in and postdocs. So we hope to continue this effort.
Okay. Thank you. I think that Christos probably.
Yeah. So Christos student or Christos can join anything, or if they have questions, maybe.
Okay. Do you have some questions before start of the Christos presentation? Oh. Maybe not.
Hi, this is Chris Elliott. I have a quick question for you. Thanks for your presentation. Very exciting work. In terms of the perception errors and uncertainties that you're modeling, that's outstanding. What about other types of failures and disturbances in your PX4 simulation environment? In terms of disturbances, gusts, actuator failures is my first question. And I'm also just interested in how you interact with your closed loop simulation. You showed some inceptors in your MATLAB Simulink model. Do you have the ability to have a human interact with the autonomy in your simulation?
I think so, because we need to work on it. But I think that the MATLAB Simulink, you can actually click the manual switch to change some signal even in the middle of the simulation, right? And then also, I remember that you can change some gain in the Simulink in the middle of the running time. But as we move towards a more serious implementation, then we have to get away from MATLAB, because the algorithm implemented in Simulink need to be migrated into C++ code that can be actually downloaded into Autopilot. software. And at this point, then we can still use this ROS environment. In the ROS environment, human can actually send out the message to this communication bus. And then we can add some service requests in their script. So then we can do this. And to answer your first question about the disturbance, I remember that I need to search more, but because this PX4 development and the community is already very large, and then they have tested a lot of different situations already. I think that probably include even wind gusts. And then one thing that I really know is that they have some of the sensor noise in the usual GPS that goes into the extended Kalman filter in the autopilot. I know that part, and also in the simulator they can add this wind in the gazebo. So those are already available. I think that adding the features usually takes time in the simulation. We just need to set some priorities. And then if you ask me if we can do those new features, yes, it's possible, but we always need to set some priorities. Thank you.
I understand. Great work. Thank you.
Thank you, Hyung-Jin. This is Lin. Can you hear me?
Yes, I hear you.
Hi, Hyung-Jin. This is very interesting simulator, and it is very high fidelity. I'm recently reading some related work on like verification for high fidelity simulation system, and maybe I need to catch up with more details about your current simulator. And could we schedule a follow-up meeting or to discuss?
Sure.
I was thinking to do some verification work on top of the simulator would be very interesting. And since we can do more flying conditions like a GPS denied or GPS jamming, and we can like guarantee the performance of the overall system, that would be very interesting direction. And maybe we can schedule a meeting this today or maybe next week.
Sure, I look forward to it. And then also, I had a meeting with through Professor Salapaka. We had a meeting with Professor Sayan Mitra, and then he already introduced this verse library.
Yeah.
And then I told them to use it as soon as possible. It is delayed, sorry, but I think we can continue. Yes, thank you.
Yeah.
Yeah.
Sure. Thanks.
I think that Prateek is ready to present, and if you do not have questions, then we can let them start.
Right. So Prateek is Christos.
Yes, his student. Let me stop sharing. Prateek, I think you're ready.
Sure, I'll start. I'm hoping you can see the screen.
Yes, I see it.
Okay, perfect. All right. Hi, everyone. I'm Prateek. I'm a student with Dr. Christos Papachristos, and we are responsible for system integration and field deployment verification of the systems that will be developed. I'll be just talking about the systems that we are currently using, and essentially we have small scale systems that we have already deployed. We have medium scale systems that we are developing right now, and also we are moving towards heavy scale systems, which I will be presenting soon. So we have Mini Hawk hybrid VTOL and fixed wing airplane. So this is essentially a tilt rotor system which can transition into forward flight and also take off vertically and land vertically as well. We have autonomous sensors over here, which comprise of essentially GPS unit, Intel RealSense for VIO, and as well as we have RGB camera on board, which we can use for any kind of detection or perception. Furthermore, we have CADAS-WIM 3. It's essentially a 6-core compute board. Essentially, it also has 5 TOPS NPU. which allows it to essentially implement neural networks. We also have a power management unit over here, which allows this aircraft to essentially hibernate over a long period of time. And essentially it leverages these solar panels to replenish its energy resources. Right. We also have some work with ICRA that we published over the past 6 months. So I can play the video. So this was essentially during the mosquito fire, where there was a huge cloud coverage, and we demonstrate over here a repeatable autonomous system, which essentially can operate without any human intervention. Yeah, I'll just skip to the more interesting part right now. Right, during the first leg of mission, the autonomous vehicle essentially surveys and lands as soon as the energy resources are depleting. And with the power management board that we have on board, it has the ability to essentially hibernate once there's no solar energy available. And as soon as we have some solar energy back, it can start recharging again to go over for the next leg of mission. And we have essentially field tested and deployed these systems and verified that they work. Right, once it's recharged, it's ready to go for the another leg of mission. And I guess this repeats for the next leg of missions as well. So I think I can skip to more interesting videos moving forward. Right, these are another set of work that we did with the micro aerial vehicle that we have on board. And this is more towards autonomous detection and deep learning based algorithms that we can essentially deploy on board. What we do essentially over here is it's simple YOLO detector, which are essentially catered towards finding landing sites which are suitable for the micro aerial vehicle to land. And also we have some work where we can detect another system of system which can be used as marsupial system to extend the operational period of Minihawk. By combining these modalities, we essentially are able to recharge the system within 30 minutes as opposed to 3 or 4 hours where we are just wasting a lot of time where vehicle is just sitting idle. For the mid-scale system that we're developing right now, we have a similar configuration where we have GPS unit on board. We also have Intel Vio systems, which help us in localization. We have RGB cameras as well, and we are also looking to mount a LiDAR camera, LiDAR system, and we are simply looking at this point if that's a possibility. Over here we have another set of compute board, which are Firefly Rock RK3588S, and it is a bit more powerful since it has 8 cores and it also supports 6 TOPS NPU. So essentially a more powerful unit to deploy neural networks on board as well. We are also looking to make this waterproof so that it can be deployed overseas in the event that we are not able to find any suitable place on the land. We can probably land it over water bodies as well. And this is another paper regarding the mid-size aerial vehicle. This was accepted as ICUAS and it's attributed to the NASA project as well. And over here we demonstrate that the initial design of the vehicle. Right, so essentially all the behaviors that it can take off, the so this is just the VTOL configuration where it can operate, and it's just a simple waypoint following mission. And next we have essentially, let me back up a little bit. Right, next we have the fixed wing configuration where it can fly for longer period of time. So all these systems are essentially field deployed and tested. Further, we are moving into heavy payload commercial multi-copter, and this is essentially commercially available DJI system. We are also in the process of mounting LiDAR and other perception units like RGB camera so that we can have our own planning and perception algorithm run on board. Over here, we have a much more powerful compute unit, which is the Intel NUC 9, and it's essentially 4 cores and an i7 processor. And we have a DJI autopilot over here, which we are interfacing with the ROS. Right, and this is the video of some initial system identification sequences that we captured, and we are essentially moving towards having perception, planning, and onboard MPC. Furthermore, we have some educational content, so essentially a simulation for aerial robotics course. We have set up a digital twin for the Mini-Hawk system that we have in the lab. And essentially we're using ArduPilot, Gazebo, and ROS to interface all the systems over here. And again, this is essentially publicly available on GitHub. Thank you.
Is it all? Thank you. Thank you. So let's see if there are any questions here now.
Hi, Prateek. I have a question here.
Sure.
First of all, thank you for the excellent presentation. Looks very exciting. You mentioned there is MPC running on board for the heavy payload experiment, right?
We are in the process of deploying the MPC. The video that you saw was for system identification right now.
Oh, I see.
That, yeah.
Okay. And may I ask what computational power you would have on that drone to enable MPC real-time solving?
So as you saw in the slide, we have Intel NUC, which is i7 processor and it's 4 cores. So I guess that gives you an idea of the compute power that's available on board.
Mm-hmm. Mm-hmm.
And
Yeah, we
to give you more information, I think that's 11th gen i7 G7.
I see. I see. Okay. Thanks for that. We also have some development on the Quadratron MPC in our lab. So I think we can chat offline to, share some experience. One thing we don't have is this outdoor flying facility drones for testing scenarios. So it will be interesting to see what we can do together on that regard.
Sure, yeah, that'll be great.
Mm-hmm. Right. Thanks.
Hi, Prateek.
Yes.
So your lab already have used LiDAR sensors with the aerial vehicle in that subterranean challenges,
Yes.
right?
Yes, we have.
So you are already capable of doing it.
Yeah,
The test
we
planning
have
and
experience with
yeah.
different LiDARs as well, Ouster LiDARs, VLP, and it ranges from even 32 channel 1 to 128 channel.
Is there some difficulties or challenges to change the environment from the mine to the open space, or nothing is need to be worried about? Can you give me some your insight or
So
idea?
mines would be more challenging if you're talking about LiDAR because it could be self-symmetrical structure. So essentially, when you have a LiDAR and you have a long self-symmetrical structure like a cylinder, so you'll have some localization error because there are no specific features on board as well. So you have to have other modalities, even with regular RGB cameras. There is some kind of drift because you might not be able to find some features. So what we have with the other drones over here is we have thermal cameras. So we are able to use thermal cameras to essentially have some features in the underground tunnel.
I see. But you are not saying that the outdoor navigation is much easier than the subterranean navigation, right?
Fair, yes. Yeah, I mean, outdoor has its own challenges for sure.
Okay. Thank you. Oh.
Do we have more questions?
By the way,
Hi,
Prateek.
Yes.
Prateek, sorry. There is a question by Areen in the chat.
Okay.
Maybe it's to both of us, and maybe you know it better than I know. But she asks, is the version of ROS that we are using suitable for real time?
Right.
What do you say about the real time capability of ROS? What do you think? Maybe you know more technical details.
Yeah, I mean, ROS is essentially, so we are using ROS 1, if that's what you're asking. We have not moved to ROS 2 yet. But yes, all the systems that you see over here are working real time, and even with the small compute board that you saw with the micro aerial vehicle, we are able to run all our algorithms real time. So that's not an issue at all.
But isn't it like for the control loop around like kilohertz or 100 hertz, that they are rather not use this communication bus by ROS state, but use different memory access, right? Or
So
like a
for running
IMU to controller kind of, yes.
For running higher level controller, we are essentially deploying on the flight controller unit that you may have seen in the slides. So we're using Papachristos Pro. So all the control algorithms which need to run on higher rate are running over there.
Okay.
And if we essentially want to use not a low level controller, but rather a higher level controller, those can be run at around 100 hertz.
Yeah, I agree. Yes.
Yeah, but definitely not 400 or 1000 hertz.
Okay.
Okay, if no more questions, I would like us to ask Sayan to introduce his colleague from Boeing, Aaron, to see what Aaron has to share with us regarding the Boeing opportunities, since Sayan has this visitor and he has approached Sayan with a request. Sayan, can we get, I don't know, do we need screen sharing or you just talk? I'm not sure. Hi. Hello.
Hi, everyone. Thanks again for the great presentations. I have the pleasure of having Aaron Main from Boeing here visiting us today. He's a senior research engineer at Boeing, Boeing Research and Technologies, and he's in working very actively in this autonomy space. So can you hear me okay? All right, great. Aaron.
All right, thanks. I didn't have anything like specifically prepared. I just kind of, when I was going to come to campus today, I said to Cheyenne that I wouldn't mind, getting an update on what this ULI was doing, since when I remember when you guys were putting it together, I was in a couple meetings about it. My colleagues, Wafang Yu, I know is on your steering committee. We might have another person from Boeing on that. So I'll kind of leave the critical direction up to them, but just kind of tell you what I'm interested in learning from it. And even before that, I'll give you just a snippet of the areas I'm working on. Before even I want to say that, though, I wanted to share a note I wrote down here, and it ties into the Irene's last question, right? I did see recently that, so Wind River makes VxWorks, which is a real-time operating system, right? Hard real-time. I think it's an ARINC 653, which is an aviation standard for that, like partitioning and real-time structure. And they have a version that is running, I think it's ROS 2, and I think it's part of the like ROS for industry or whatever that program they have. Now, VxWorks is expensive. It's not freely available Ubuntu, right? But there is a path for getting, or at least as I've seen, there's a path for getting things that are done in ROS ported over onto hard real-time operating systems, which can be used for certifiable avionics and compute and stuff like that. So I wanted to share that since we were talking about it. I guess, like I said, I don't want to give any hard direction here, but I think in general, the things I'm interested in learning from the ULI and what's going on here is where, I guess, the knowledge base here sees the gaps, right? What gaps they see in going from the state of the technology now to the point where we can actually, or where we can, I don't want to even call it guarantees, but to where we can generate evidence throughout the tool stacks of the safety, reliability, performance of systems. And just kind of some examples we'll go through, or that I'll give here in some of the things I saw in the presentation today, like starting with the game engines, right? I know their big business is video games. I know a lot of automotive manufacturers are using them. In aerospace, right, when you get into simulation tools and things you're using to build your software, right, there's whole processes and industry standards for qualifying those tool sets before you can use them to generate evidence for certification or even waivers to certification and things like that. And so I think someone's trying to talk and is on mute there. We can't hear him, Cheyenne. Unless they're discussing it amongst themselves. Okay. Right. And so that's kind of, one of the first things I think, and I know, right, are these tools that are being used to develop the systems, right? Are they capable? Not that I'm expecting, this work, but are there any hard gaps in the way those tools work, the way they're developed, that are gonna inhibit, the qualification of them for using to develop, safe, in the end, safety critical applications, right? And then in the more recent presentation, go ahead.
Sorry, if I may, just for clarify, when we talk about tools, right? I kind of look at it as two sets of tools. There's the simulation, and the real engines are really nice for development of algorithms, etc. And then there's the algorithms themselves.
Yeah.
Right. So which tools are we talking about? Are you talking about simulation tools used for development, which clearly are not going to be Class D sims, nor are they, you know, there's just no budgets for it, nor do I think they're necessary. Or are you talking about the algorithms that are being developed?
So I was going to kind of get to that's the second part, but the Unreal Engine was the kind of the sim example, right? There's qualification around that, and I know there are, we'll put it this way, there are issues, especially in machine learn, but even in other things, in transitioning learning from simulated environments to real environments, right? And just understanding where this community thinks those gaps are in the existing tool sets, what's going to hold up, you know, our regulators or things like that on actually trusting, or our industry on trusting those tool sets that we use in the entire learning stack, right? Then when you, like Irene, as you said, when you get into the algorithmic layer, the software layer, right? Traditionally, we've relied in aerospace on formal guarantees, formal methods for, you know, going up your design assurance layers. And I know those don't apply. We don't understand those, but what is that gap in bridging the, whether it's the empirical or stochastic methods into, you know, into, we know enough about these systems that we can, you know, confidently enough replace some of the formal guarantees, you know, down the road, right? And what are the specific gaps near and far term that we will need to overcome there? And then kind of lastly, the thing I think about a lot. So in my work right now, I'm working a lot on our collision avoidance, and not just air traffic, but air traffic, ground, landing hazards, things like that, right? That collision avoidance stuff, I'm working with our internal defense programs. I'm working a little bit with our WISC joint venture, right? And so there's another piece of this that we talk about but don't address a lot, which is the actual, like, how do we see that the operational decisions, right, that these agents are making both play well together internally within its system, and then when you get multiples of these systems, and then interacting with traditional systems in the environment, right? What are the gaps in knowing that these new machine-driven systems and machine-driven decision-making are integrating safely, efficiently, not disrupting more than necessary, right? Not disrupting the other users of those environments. Right. So those are kind of the big topics that I think about, and I like to see and learn from, from you guys.
So if I may just clarify your last statement about when machine learning based algorithms, let's say vehicles, are flying in the heterogeneous environment, let's say today's airspace, how do you ensure that they do not basically become a problem?
Yes.
Is that a fair description? So if I would turn the question a little bit differently, how do you ensure that your autonomous vehicles, machine learning or otherwise, actually behave in a appropriate way, and appropriate ways defined by the user community?
Yeah, that would be. And so an example I'll give here really specifically, we did, so at Boeing, we had a DARPA program, right? And there's a bunch of stuff going on. It was assured autonomy, right? And we had a machine learned, collision avoidance DA algorithm running. We had our own internal analytical solution, basically, as a part of this test. And our analytical solution, right, couldn't find a path to resolve the conflict as we had set it up that went with the way we had encoded the rules of right-of-way, right? What the machine learned thing, that it found a solution, but the solution, as our test pilots looked at it, were like, well, that's not what you would do in the airspace. That's not what people were, because it started doing basically time-wasting maneuvers in order to wait and get, go behind the vehicle coming from the right type of thing, right? And it's those, I won't even call them corner cases, but those kind of behaviors that, while they may meet safety criteria, while they may meet encodings of rules, we don't really understand them until we actually see. And then you get into a situation where, hey, your vehicle is making these time-wasting maneuvers, but the other vehicles, which have human pilots on them or whatever, are wondering what these are doing, or if this vehicle, in like the case of our Whisk joint venture has passengers on it, right? How long before somebody takes one of these rides where it has all these time wasting maneuvers and they say, these things don't know what they're doing, I'm never doing this again. Right, and again, those are very high level abstractions of that, and there's much more technical details. But that's kind of what I wanted to share as I was seeing your work here, is the things that I think about as we're going through our work and as I see the work you guys are doing there, right? And I think the work you're doing is getting towards those things, but I think I would respect your guys' expertise here in helping us understand where those gaps are between, what you guys are doing in the research community and then what we in industry need to figure out from there to make those.
Thank you, Aaron. Thank you for sharing your perspective. And since we are at the top of the hour, I wonder if there are any last-minute questions from others that we could kind of take and maybe wrap up today's meeting. Slides and presentation are recorded and will be posted online. Any questions? If none, thank you all for interesting talks and discussions today. I hope something can continue after the meeting in between the groups, and have a good weekend then. Watch for the links I will share maybe by Monday. Okay, thank you. Thank you.